right, so we're back on KSP here, and for this video, I'm just adjusting my light here. I'm going to be talking about comparing KSP values and then doing a problem having to do with something in a dissolving in something besides water. So first off, I need you to go to your book and find page 1104. 1104 is going to have a table of KSP values of different ionic salts, and these are going to be in powers of 10. So please recognize silver iodide has a KSP of 8.3 times 10 to the negative 17th. Calcium sulfate has a KSP of 2.4 times 10 to the negative 5th. So by looking at the power of 10, we could see that this is a larger power of 10. So that means calcium sulfate dissolves more readily, is more soluble than a silver iodide. And you can look at each one of these by the power of 10. But if you have a second example like this one, copper 2 sulfide and silver sulfide, KSP 6 times 10 to the negative 37th, 10 to the negative 51. Neither one of these really break up all that much, but I can't compare because I have different number of ions. So I have 2 ions here for my copper 2 sulfide, and I only have 3 ions here. So you would really have to look at, this is going to be an S2 and this is going to be a 4S3 in terms of the calculation. So you would actually have to go through the calculation and see what your value of S in order for you to compare, since it is not a one-to-one relationship comparing both of those. So the other thing I want to do on this video is kind of work through a problem with solubility having to do with something that is not in water. So typically when you do a KSP problem, you could always assume water, but in this case, I am doing things in a sodium chloride solution. So I have lead 2 chloride. I have a KSP value of 2 times 10 to the negative 5th. I want to know the molar solubility, again, S. How much does it break up in a 1 molar sodium chloride solution? Well, this is what we call the common ion effect. And again, we talked about this in acid-base chemistry. It is very prominent in KSP as well. So that's why it's an important thing. So this KSP here is in water. And you could always assume, even in the example I just talked about, this is always how much it dissolves in water. So you could always assume that. But if I'm in sodium chloride, that's going to give me a common ion, especially since this has chloride in it, this has chloride in it, so I need to worry about that. So again, sodium chloride solution is going to break up into sodium ions and chloride ions. And again, the sodium doesn't matter, the chloride is what matters. So that concentration of that sodium chloride is the concentration of the chloride. So if I take my KSP and I have my solid and it's breaking up into lead ions and 2 chloride ions, when I'm looking at doing a KSP type calculation, I can't assume that these are starting at 0 anymore. This one's starting at 0, but because I'm dissolving this in sodium chloride, this is starting at 1 molar. So that's where this is going to be a kind of a common ion discussion. So again, this is going to be S. You can make that X if you like that better. And then this is going to be 1 plus, but you have to realize that there are 2 chloride ions. So this is going to be 2S. So typically this is going to be S and then 2S, but because I'm starting with 1 molar, it's going to be 1 plus 2S. So if I have my KSP is equal to my lead ions in brackets, and then chloride in brackets as well to the power of 2. And again, it feels like it's redundant. I'm going to take my KSP, 2 times 10 to the negative 5th is equal to my S, 1 plus 2S squared. Okay. So again, this S is going to be relatively small. So if I happen to add it to 1, it's probably going to make absolutely no difference. So I'm going to cross out this S, and I know you hate that when I do that, but it's going to make the math a lot nicer. So this is 1 squared, so S is going to be equal to 2 times 10 to the negative 5th. Again, the S is so small, adding it to 1 is going to make no difference. Okay, so what is that? That is the concentration of my lead ions. But what if I want to know what the concentration of the chloride is? Well, chloride is going to be 1 plus 2 times this value, but realize that that is essentially your original concentration of 1 molar. Okay, now you might be going, well, why am I going to have to do this problem? Well, it's kind of in comparison to how would this look in a water solution. So I'm going to do the exact same thing, but I'm going to do it in water. And so it's not going to have the common ion in there. It's just going to be our traditional one that you have in the previous video. And we walked through these calculations before. So I have an S and a 2S. I'll bring that down a little bit just for comparison here. So I have an S and a 2S, and that 2S is going to be squared. So this is going to be, again, a 4S cubed kind of situation. So you're going to divide both sides by 4 and take the cube root. S comes out to be about 1.7 times 10 to the negative second molarity. That's going to be your lead ion concentration. Okay. Now, why I'm having this conversation, okay? 10 to the negative 2 is a bigger number than 10 to the negative 5, okay? We are comparing lead in water compared to lead in a sodium chloride solution. So I have more lead if it's just in water than if I had it in a sodium chloride solution. Well, does that make sense? Well, if I am dumping a bunch of chloride into this equilibrium, which way is it going to shift it? It's going to shift it to the left, which means you're going to have less of these two ions dissolved in the solution. Okay, so that means I'm going to have more in the precipitate side than the ion side. So my lead concentration should be a smaller number than I would have in pure water. That is demonstrated here by the difference in those concentrations of lead.